In this video, we'll take some examples from the course text to understand the mechanics behind uh, the computation of convolution for LTI systems. So to start with, this is example 2.6 from the course text. So what it says that let xt be the input to an LTI system with a unit impulse response ht, where xt and ht are defined as such. So xt is basically a decaying exponential signal where a is some positive quantity. Okay, ht is a unit step the unit step function ut. So that is 1 for t greater than 0. The situation is as such. So you have an LTI system. It's a continuous time LTI system. So it is handling continuous time signals, right? So the first thing you want to do for the given characterization is to introduce a direct delta function, okay, delta t, and the impulse response is denoted by ht for this system. Ht is the output for delta t is ut. Okay, so if you feed delta t to the system, the output is ut. Okay, now for any arbitrary input, call it xt. For any arbitrary input, call it xt. The output will be given by the convolution integral. Okay, so yt can be expressed for any given xt as now in terms of ht as integration in general from infinity to plus infinity x tau h of t minus tau h of t minus tau d tau. So you see the integrand is the multiplication of the two signals x tau ht minus tau. Ht minus tau is the basically the time shifted and the flipped version of the impulse response, and it has to this the area under this integrand is the convolution integral. Okay, this is the integrand, right? So in general, this is from minus infinity to plus infinity. Well, you can remodify these limits according to uh, given impulse response and the considering the time limits of the input signal that we are considering. So for example, if you're considering this integrand is shown over here, right? I mean, what happens is that this x tau h of t minus tau can be written as analytically. You can write this as x tau is, this will be e of minus exponential e minus a tau u tau. Okay, you just change the variable of integration. Tau is also a time variable. Okay, it's a dummy time variable. Then ht minus tau will be u of t minus tau. Okay, ut minus tau means graphically what it means is that this will have a depiction of something like this. I mean, if this is the vertical axis, okay, and this is your horizontal axis of time tau, then this is simply shifted. This is a flipped and shifted version. So this t is because u minus tau is flipped around tau equal to 0. Okay, this u of tau will exist for tau greater than equal to 0. Okay, tau greater than equal to 0, and u minus tau will be just the flip version of u tau. Okay, and then if t is greater than 0, if this is if t is greater than 0, so then this is a flipped and time shifted version of your impulse response ht. Okay, so this graph depicts u of t minus tau precisely. Okay, but in other case, what if t is negative? What if you're considering the values of the negative time? Then the situation is the shift is going to be towards left. Okay, so the shift is going to be towards left. So this is t. Now t is less than 0. Okay, and this depicts again ut minus tau for negative time, right? So that means if you multiply these two, well, it's only non-zero. Well, it will be 0 because this signal it exists for only for tau greater than 0. So you can see the regions of time where this is overlapping, and this overlapping only occurs for where t is positive. Okay, where t is positive. But it's 0. But for example, if you look at this graph over here, there's no overlapping for the signal x tau. Okay, for the signal x tau. That means for negative time, this integrand is 0. Okay, but for positive, when t is positive, then you have certain area to integrate. Okay, so you see this will be e minus a tau, and then I can write this as ut minus tau as well. Okay, because that's the area common, ut minus tau. So, or if you don't want to write this, then that means your t is a positive quantity. So, of course, tau is the variable of time. So we are considering this for positive values of t. So tau is between 0 to t. Okay, 0 to t. This is what is mentioned over here. But for t less than 0, there is no overlapping, so basically the integrand is 0. The integrand is 0. This is also depicted in figure 2.17. And this is for h tau, which is primarily u tau. Okay, this is a unit step function. And for x tau, this was a decaying exponential. It was of the form e minus a tau, u tau. Okay. So this is decaying with the variable tau, all right, and a is a positive quantity. Remember that. If a is a negative quantity, then it would be growing. Okay, so it would have a growing situation like this from 1, because tau equal to 0 exponential is 1, u0 is also 1, but for as tau grows, okay, so this approaches infinity, your function x tau becomes 0, right? So this is decaying for positive quantity a. Now ht minus tau is basically your ut minus tau. This is ut minus tau. So for t less than 0, this is the shift is towards left for negative time, but for positive time, uh, for positive time, the shift is towards right. Okay, the shift is towards right, and you can see from here, if you consider the output of the system yt to the input xt, which is given by the convolution integral x tau, h of t minus tau, this integrand, this multiplication, we are interested in this function x tau ht minus tau. Okay, this has to be integrated. So the multiplication is basically 0 for t less than 0, because there is no overlapping between x tau and ht minus tau. So for t less than 0, your yt is precisely 0. You see, there is no overlapping. If you consider this curve and this curve, okay, so x tau and ht minus tau has no overlapping for t less than 0. So basically your yt is 0 for t less than 0. But however, for t greater than 0, well, there is an overlapping, certain overlapping regions like this. Okay, and you have to multiply this x tau. Basically, you have to multiply x tau with the ht minus tau, and if you do that over here, okay, it will be something like this. It will be a piece of the signal which multiplies like this, and then you forget about the rest of the signal. But as t is greater, but as t is growing, you can visualize that yt. If I don't write this as analytically, if you keep on sliding this, the flipped and the time shifted, if you keep on sliding or shifting the flipped impulse response h minus tau for positive time values, the curve of yt is going to grow first. Okay, and it's going to grow as a limit to a certain value, because your xt is decaying, right? I mean, you just okay, let's call this t1, and then have another shift t2. Obviously t2 is greater than t1. That means there is more overlapping. But if you consider the overlapping over here, this overlapping region It's decaying. It's also decaying with time. Okay, so the rise is going to be asymptotically reaching a certain value where the signal x tau is going to vanish. Okay, so graphically you're shifting this. Okay, so t3 is greater than t2 and t2 is greater than t1. So let's say at t1 you have a certain region that is overlapping. At t2 there is more overlap. T2 t3 is there is more overlap, even more overlap. But then since x tau is also decaying, that means the output y of t will be limited, okay, by a certain value. Y of t will be limited by a certain value. So that would be the case. But analytically, if you have to solve this, then you can carry out the integration. This is a simple exponential function, and if you do that in this region, okay, so basically you have to integrate this x tau uh, h of t minus tau, sorry, t minus tau d tau. Well, this integration is equal to e of minus a tau, okay, e minus a tau, and again you have to consider for the positive values of t, right? So this will be from 0 for t greater than 0. T is greater than 0. T is a variable, okay, but that keeps on sliding, okay. So the shift has to be towards right, and t should be a positive quantity. That means if you carry out this integration, this will be minus 1 over a, and this will be e minus at minus 1, okay. And if I have to write this again, that this result is valid for t greater than 0, because you know for t less than 0 there is no overlap, and for t greater than or equal to 0 the yt exists, otherwise it doesn't exist, okay. This is my yt, okay. Then you can see that this yt is approaching a certain limit, okay. Now if you want to rearrange this can be written as 1 over a, which is a certain positive quantity, finite and positive quantity 1. It becomes 1 minus e of minus at. And you can see this clearly, that as a limit, when t approaches infinity, your y of t approaches 1 over a, right? Your y of t approaches 1 over a. So that's the limit, because your x of t is a decaying function. So the area that is to be integrated is also it is accumulating, but then it is accumulating to a certain limit, and this limit will be 1 over a, okay. This limit is 1 over a. So if you see from here, if you do the integration, well, this is from 0, and this is, you're considering this for t, the positive values of t, okay. You carry out the integration and you're left with the same function. Y of t is given as 1 over a, 1 minus e minus at ut. So this exists, again, yt exists for t greater than 0, or you can write this as ut. But as a limit when t approaches infinity, well, the area that is to be accumulated under the curve is it becomes finite, okay. This becomes equal to 1 over a. This is over here, right? So this is the response of the system in 2.6 example, with the impulse response ht is equal to ut and the input xt equal to e minus at ut. Okay, so you must remember that for an LTI system, all you need to do is find, or if it is given, in case, or the, like in this case ht was given, if you introduce a direct delta function delta t, just see what is the output. In this case it was ut, and all you need is the impulse response, and then then you should know that since the characterization of the system is both linear and time invariant, well, then the output should be given by the convolution sum, which we have derived in the previous 2 lectures, okay. And this convolution sum can be evaluated in terms of the impulse response, right? So you just have to consider the flipped and time shifted version of that impulse response, and you see where this overlapping occurs, and just go on integrating that area, okay. So this integration is done for t greater than 0, and we have shown here that for this integration, the area under the curve is rising, as a limit. As t approaches infinity, well, this becomes equal to 1 over a, okay. So all you need to do is you need to consider the impulse response. Once you have the impulse response, just flip it over and then see for which regions of t there is an overlap between x tau and h t minus tau. So in this case, for t less than 0, yt is 0, but however for t greater than 0, there's a non-zero overlap, and then you can integrate this, and visually you can see that you can visualize that yt will be growing function as with the positive values of t on the time. It continues growing, and then you have it reaches a limit because xt is decaying, and that limit is 1 over a in this example. Okay, that's all.